Okay, welcome to Surgical Robotics Lab 7. In this lab, we're going to be using Newton's method for teleoperation. So we'll be communicating between the haptic device and the robot. And we'll also be using the mechanistic gripper end effector attachment as well, just to give you guys some ideas for the project as well. So the way that the communication between the haptic device and the robot will work in MATLAB is we're going to set up the port for the haptic device by itself and also the Ethernet connection to the robot by itself. And then we're going to scale the workspace of the haptic device to that of the robot, just like and linearly map one workspace to another, so that as we sample the position and velocity from the haptic device, we can tell it to go to the corresponding point in the mechanisms workspace. In the first activity, we're just going to work on scaling the workspace, and we're not going to use Newton's method. We're going to use Mechademic's built-in move pose and move lin commands. And this is what that will look like. I'm going to go ahead and download the student folder, and it'll zip it, and I'll get back to you when it's open in MATLAB. So this is the unzipped folder that we've got here. You can open, let's try Lab 7 Part 1. We'll open that one up in MATLAB, and it should just bring me to the correct folder. And we need all of these other things as the driver files for the haptic device. So this is what it'll look like for you guys. You guys are just going to fill in the blanks for a couple commands here. I'm just going to make sure that I'm actually connected to the right port for the haptic device. Should be good. So all I have to do here is experiment with how to scale the velocity linearly based on what I'm measuring from the haptic device, and how I should scale the X and Y values of the position. And then we're just going to use the move lin command to get places. Your robot is probably going to start in a zeroed position, which means it might be smart to move its joints so that it's not going to be in a singularity for the use of the move lin command right away. So I'll do that right now. I'll give it a right line T, move joints, and then I'll put it somewhere where I would expect it to be. Let's try like 0, 50, 10, 55, 0. Something like this should put it in a reasonable position. So I'll just get the robot set up here for you. We'll turn it on. Okay. And then we'll home it. All right. So that's what a robot looks like right now. I'll zero the joints and switch to monitoring. Okay, so this is what we've got in MATLAB. I'll change this to 100 because that's the robot we're communicating with. I've sort of messed around with it a bit to make sure that everything's working. So what's happening here is we're just gonna iterate through sampling the haptic device's position and velocity in the X, Y, and Z direction. We're saying that our velocity is equal to the magnitude of the vector of all of its velocities, and then we're going to scale the robot's Cartesian velocity in millimeters per second as some linear function of the magnitude of the haptic device's velocity. So I'll use something like 350 times velocity plus some constant 50. And to scale the X and the Y positions, I'll do something like 190 minus 450 position 2 190 minus 450 times position 2. And the reason that we're using position 2 here and we'll use position 1 here is because this is the way that I've set it up. You guys don't need to do this, but as you guys know from the last lab, Y comes out this way and X is this way with the haptic device. So the robot's X is going to be going to the right based on the screen, and that's the Y direction for the haptic device. So I'll do that, and then I'll try using maybe just 450 times position 1 plus 0.05. You guys can start with this. This is just what I'm using because I know that it works, but you can certainly make a nicer linear mapping of the workspaces. But we'll just run this and we'll see how it goes. So we would expect it to first move its joints to this, and then afterwards we would expect it to start following the haptic device. So I'll do that for you guys. You'll notice that I've got the gripper on the robot already. That's for the next activity, so it's not important for this one. You might not even want to put it on the robot until you've done that, but it doesn't make a difference. So I'll home the haptic device, and I'll run the script and we'll see what happens. So at this point, this GUI's popped up, and you can start by pressing the spacebar. Or clicking on it, I guess. So it's moved its joints, and now we're going to do teleoperation with it. So I've set this to have a pretty mild Z mapping. Once you guys are comfortable with it, you can change it, but this is just so that you guys don't pick up the haptic device, start the program, and slam the robot into the table. But since you're using move lin, it's pretty good, and you are keeping the Euler angles constant even in between the samples. So this is what it looks like. You can scale your velocity mapping as well so that it's more responsive. This is okay, but there's a little bit of a delay. So let's switch that to move pose, because that's what I think the next part of the manual is going to tell us to do. Yeah, so we have gone through the theory, and then we've used move lin for activity 1, and we're going to switch that to move pose. And we want to see what the difference is. So if I were to go to MATLAB, I've got all of these strings initialized sort of here, because in MATLAB you've got to concatenate these strings yourself. I don't think that there's a Macademic toolbox for it. But we'll just change the move lin one to move pose. And we'll run it again. We'll see what happens. We'll go like this. So it's moved there. It's a little bit smoother. It's got kind of a delay. But if you were to move fast, or if your velocity mapping weren't quite great, you might expect to see some change in Euler angles, because it's not going to move in a straight line anymore. So just something to observe the differences with, and then to toy around with to map your workspace. That way, if you guys are going to do teleoperation for the design project, you've got Newton's method down, or you can use Macademic stuff, and you also know how to map the workspace. You can focus on the biomed application. So there's that. And we'll move on to activity 2, which uses the gripper. All right, so the next activity, we're going to actually use the Jacobian. It's going to be modified slightly from what you guys have seen in lecture. The top half of the Jacobian is going to be with respect to the flanges X, Y, and Z. And since in this lab we just want to keep the end effector of the robot having Euler angles 0, 90, and 0, we're just going to use the wrist coordinates of the robot in the bottom of the Jacobian. And it sort of works out the same way. So we can keep the Euler angles constant the entire time, or we can change it if we'd like. But since we know how to get the wrist of the robot based on the flange and the desired Euler angles by moving back along the third column vector of the rotation matrix made by the Euler angles, we could just do it this way. The only caveat is in Newton's method, when we don't account for the Euler angles and instead we account for the wrist, we end up differentiating out theta 6. So instead of just doing the forward kinematics along the bottom of the loop, we're going to compute the Euler angles, and then since theta 6 will only affect gamma, we're just going to adjust that joint based on the difference in gamma between the desired and actual, and then after the adjustment of theta 6, we'll do the forward kinematics. You guys don't have to do this because the Newton's method script is written for you guys. There are just a few things that you guys have to do to fill out the blanks. So I'll show you how to do that. So this is the main script, and it's going to look something very similar to what you did in the previous activity. You guys are just going to fill in the velocity mapping and the position mapping. We've also got this gripper stuff up here, which we'll go over in just a sec, but first I'm going to explain the Jacobian. So since we're using the Newton's method in this one, we're going to be giving the robot move joints commands rather than move lin or move pose commands. And you can see that here we've got Q, which is our joints, is equal to wrist ref inv kin. So we've also got this function in the folder, which is this one. I've got it open over here. The wrist ref inverse kin, we'll take this guy. So you need to figure out what the Jacobian is, and then you'll paste it in here and it'll do the Newton's method for you. Don't worry about taking the inverse because MATLAB has a built-in function that'll take the pseudo-inverse for you. You just need to use one of the other folders in this, one of the other files in this folder to determine the Jacobian. And you can do that by filling out wrist underscore 3doff underscore Jacobian. And this is what it looks like. Basically what we're saying is, okay, so the flange is given by these successive transformation matrices based on the DH parameters, and the wrist is given by this one. The wrist of the robot is at the multiplications of the transformation matrices up until h34. So I will have defined F, G, H, I, J, and K as the X, Y, Z of the flange and the X, Y, Z of the wrist. And you guys will differentiate these with respect to theta 1, 2, 3, 4, 5, and 6 and append them to some Jacobian. So I've just done that down here. Row 1. Okay, so let me divide this up for you guys. So this is each row of the Jacobian based on what you're differentiating. You won't have this, but you can just write this down. You can copy paste it. I'm sure you can find a faster way to do it. But the syntax is diff, and then what you want to differentiate and what you want to differentiate with respect to. So we've got the symbolic variables theta 1 through 6 up here, and they are in the elements F, G, H, I, J, K, which represent X, Y, Z of the flange and wrist. And then you'll differentiate each one, and I've labeled them like row 1, column 1, and so on, so that I know what to put in the Jacobian over here, which will also be empty for you guys. So you'll run this script and you'll end up getting some ridiculous looking matrix, but I think it's good to see how big the Jacobian is to understand sort of what you're dealing with. So I've completed the script and I'll run it. And this is my Jacobian. It's this gigantic matrix down here. So what you'll do is you'll copy paste that into your wrist ref inverse kin where it tells you to. And I'll just do that here. The reason I'm getting you guys to copy paste it is because we could make a function call to this one, but MATLAB doesn't take too kindly to calling symbolic returned matrices and then subbing things in while referencing the previous symbolic variables from the prior function. Maybe there's a workaround for this, but I didn't find it. So we're just going to copy paste it. Control C. Jacobian equals Control V. And you're going to want to get rid of all of these square brackets over here. And then you're going to want to go all the way over here. And you're going to want to put a semicolon and then replace all of these guys with semicolons. So that's your Jacobian, and it's in your Newton method script. So all you have to do is finish the rest of the main Lab 7 Part 2 function. So I'm just going to use the same values, although I would advise that you guys don't, because now you're using velocity as a proportion of the max speed. So I'm not sure how good this is going to look, but for the sake of an example, this is what I'm using. And then you guys are going to have to create these buttons up here. And these buttons will pop up on that blank GUI that you usually see, and it'll say either open gripper or close gripper. And the way that you're going to do that is by pasting the Mechademic command gripper open into this blank. Or sorry, I think that you guys won't have the right line T either, so you'll just have to copy paste right line T gripper open. But I'm just going to do this. Okay. So you should be good to run the second part of this lab now. Just make sure you save it. And let's just double check everything here. I've got the wrist-ref inverse kin, the big Jacobian, the pseudo-inverse, and every time I'm plugging in a new theta 1. Okay. So I'll show you what it looks like before I show you the robot. So this is what you guys will see. It's got a gripper open and a gripper close. And you'll be able to control the robot like that. So this is me using a teleoperation, and now it's using joint commands rather than Mechademic built-in commands. Well, it's using the move joints command, but I can pick up the object over there, so I'll click on the GUI and I'll open the gripper. I think it's already open. And then I'll pick this guy up. Might be a little bit far away. Close it. Pick it up, bring it over here, put it down, and open the gripper. So I think with the joint commands, it's a little bit more responsive, especially because you're using velocity control. So you've pretty much got a PD controller here. I think the delay is reduced. So you guys can sort of tune this and map it to reduce the delay. But that's what that activity looks like. And if you guys want to know how to set up the gripper, I'll show you guys that as well. Let's find a clear all here. So over here, I'll connect, and I'll give you guys a little too early gripper. Yeah, there we go. So this is what the gripper looks like. From the side, you've got a little intermediate piece of metal, which you'll have to put between the flange and the gripper. And it's got those little diamond screws, so you're gonna have to ask me for the screwdriver to put that on. And then there are just two screws in the front that you're gonna put through here. And aside from that, this wire connects to the smaller Ethernet port on the side of the wrist of the robot. And after that, you guys should be good to go. So let me tilt that up a little bit. There we go. When you want to use this in MATLAB, you have the gripper commands. It looks like right now it is open. So we'll use the gripper close command. Turn off jogging. That's the syntax for it. So I'll just run it and you guys can take a look. There you go. So that's how that works. And I believe that's everything that we have for this lab. So just a quick summary, you guys are going to first make a teleoperation script in activity 1 by scaling the velocity and workspace of the haptic device to the robot and using the move lin and move pose commands. And then afterwards, you guys are going to use Newton's method, but Newton's method has been defined for you guys. You're just going to copy paste your Jacobian into the inverse kinematic script, and then fill in the workspace again. And you'll also make these gripper buttons, which you can use to open and close the gripper. So that's it for lab 7. Good luck, guys.